So let's introduce a new concept that has to do with reactions, something that's useful. When we have a generic chemical reaction, if we know that this reaction proceeds, there's a hidden truth in this reaction, and that is that the reverse reaction doesn't proceed. I mean, it can't work both ways, right? What that also means is that you can imagine a situation where x plus y going to z doesn't happen, and it sort of suggests that z can form x plus y. This isn't exactly 100% true. I mean, you can envision a situation where a reaction doesn't proceed either way, because you're just making it up. But when we're dealing with salts, like NaCl, if it is placed into water and it ionizes into the aqueous material, because it proceeds one way, it suggests that if you have sodium ions and chloride ions, it will not be driven back this way. The reverse reaction does not take place. And we know this actually, we can form this reverse reaction. We can actually slowly evaporate out the water and the sodium and chloride will precipitate out. But for the most part, the sodium chloride is perfectly happy when it's dissolved in water. But not all ions are perfectly happy when they're placed in water with other materials. And this is where we get precipitation reactions. Right? Many ions have very limited solubility in water, particularly when they're paired with one another. Now, it turns out that we can use a number of very simple rules to look at an individual compound and predict whether it's going to be solubility. Additionally, we can look at pairs of ions, positive ions and negative ions, and predict whether they will combine together to form an insoluble salt. Again, going back to this, if the compound is not soluble, doesn't precipitate, that means that if you were to mix its individual ions, it might precipitate. So we'll actually cover a lot more about reactions like this in thermodynamics next semester, but we can use this sort of shorthand idea about reversibility of reactions to predict when you bring a series of ions together whether or not they will precipitate. And for this we need to look at the solubility rules. Now, we can spend all day talking about the solubility rules, but I can sum up the solubility rules in basically one statement. Usually, whenever you have something that's highly charged paired with something else that's also highly charged, those will probably have poor solubility. Why? Because ionic compounds are attracted to one another. The strong charges pull one another towards one another, forcing them out of solution. Usually when N and M are greater than 1, when they're both greater than 1, this material has a less likely to be soluble. And there are exceptions, lots of exceptions. There's lots of monovalent ions, +1 or -1, that do not favor solubility. But for the most part, high charge, poor solubility. So if you see a lot of +2, +3 ions, chances are good the stuff's not going to be soluble. All right, so what are the solubility rules? All right, solubility rules are follows, and you should memorize these. All right. All alkali metal salts and ammonium salts are soluble. Again, things that are composed of sodium, ammonium. Again, look, monovalent. All right, any salts composed of that are likely soluble. NaCl, NaNO3, Na2S. These are all going to be soluble. K2SO4, all going to be soluble based upon this rather simplistic rule of alkali metal salts. So it gives us a whole list of things we can pair an anion with, a negatively charged species with. All nitrates are soluble. Anything with an NO3- attached to it is going to likely be soluble. So Fe2o3 iron 2 nitrate, likely soluble. Zirconium nitrate, zirconium 4 nitrate, likely soluble, because all nitrates are soluble. Oftentimes, one of the ways you get metals salts in solution is as nitrates. All halides are soluble. Things with a chloride, an iodide, a bromide. Again, monovalent. All halides are soluble except a small handful. Silver salts, lead salts, lead-2, and mercury-1 salts. These will form insoluble halides. AgCl is the classic. PbCl2 are classic examples. If you mix silver ions and halide ions, the materials are insoluble. Lead chloride and silver chloride do not readily dissolve. So these three rules, all alkali metals, all nitrates, all halides, are typically soluble, except for silver, lead, and mercury. This will carry you through most of your material. You can assume that pretty much everything else is insoluble. Now there's some finer points. Okay, most hydroxides are insoluble. All right, so anything with an OH- is not going to be very soluble, except for those that fall under the first few, sodium hydroxide. Barium hydroxide is also one of the soluble ones. Pretty much everything else is insoluble. Phosphates, carbonates, calcium carbonate, insoluble. So for the most part, everything else is going to be insoluble. But again, there are exceptions. For instance, potassium perchlorate is actually very poor water solubility. So it has a weak water solubility. Why? Because some materials don't necessarily behave by the rules. You don't need to memorize those. You do need to memorize these rules, though. Right? So you can use these rules to make predictions on whether a material will be soluble or insoluble. Fe2o3 insoluble. Why? Well, it's not an alkali metal, it's not a nitrate, not a halide. Pretty much everything else is insoluble.